Late September 1944. A forward German position near Aracourt, France. The Panther tank commander peered through the smoke, drifting across the battlefield as his crew maneuvered a captured American Sherman into their defensive lines. This wasn't the stubby 75mm variant they'd grown accustomed to seeing. The barrel extending from the turret measured over 13 feet long, mounting a 76mm M1 gun that represented everything German intelligence had warned them to expect. What the crew didn't know was that this single captured tank would trigger a crisis of belief among experienced German tankers that no amount of technical documentation could resolve. The mathematical realities of sustained fire rates were about to collide with assumptions built from months of combat experience against earlier Sherman models, creating a psychological rupture that would force German crews to fundamentally reassess American manufacturing capability. The Sherman bore combat damage across its flanks, but its turret mechanism remained intact. Serial number USA 3010151. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. This M4A 376 had belonged to Company C of the 37th Tank Battalion, 4th Armoured Division. German recovery crews had towed it barely 3 kilometers from where its crew abandoned it during the fierce armoured engagement that characterized the Battle of Aracourt, one of the largest tank battles fought by American forces in the European theatre. Every detail revealed during the initial inspection contradicted assumptions German tankers had developed about American design philosophy. The turret traverse remained smooth and responsive. The ammunition storage showed a thoughtful layout optimizing loader efficiency. The ready ammunition rack positioned directly under the gunner's seat held 6 rounds within arm's reach, designed for rapid access during sustained engagements. German crews, trained to expect crude American solutions to complex problems, found instead evidence of systematic ergonomic engineering. Officers from the 111th Panzer Brigade gathered around this prize, notebooks in hand. They had specific orders. 7th Army Intelligence wanted detailed technical reports on the improved Sherman variant that had proven surprisingly effective against Panthers during the Aracourt fighting. The examination would proceed methodically. First, technical assessment of the gun and fire control systems. Second, ammunition analysis. Third, crew ergonomics evaluation. Finally, sustained fire rate testing under conditions approximating combat. The technical team began with careful measurements. The 76mm M1A1 gun measured 52 calibers in length, substantially longer than the 40 caliber 75mm M3 that armed most Shermans they'd encountered previously. The breech mechanism used a semi-automatic vertical sliding block that ejected spent casings automatically, requiring no manual extraction by the crew. This detail alone suggested higher potential fire rates than German designs employing manual extraction. German ordnance specialists photographed every component from multiple angles, measuring clearances with precision instruments and documenting construction techniques that seemed impossibly straightforward compared to their own methods. The gun mount demonstrated remarkable simplicity. Where German designs incorporated complex recoil systems requiring frequent maintenance and precise adjustment, the American mount achieved adequate performance through robust over-engineering and generous tolerances. The ammunition storage arrangement caught immediate attention from gunnery specialists. The turret basket floor featured a spring-loaded ready rack holding 6 rounds positioned for optimal loader access. Additional ammunition resided in protected racks beneath the turret basket and along the hull sponsons, all arranged to facilitate rapid replenishment of the ready rack during combat. The total load of 71 rounds provided substantial sustained fire capability. German tankers had extensive combat experience against the 75mm Sherman. They understood its capabilities thoroughly. Fire rate observations from multiple engagements suggested American crews achieved approximately 12 to 15 aimed shots per minute under combat conditions. Respectable, but not exceptional by German standards. The Panther, according to official documentation, could achieve 6 to 8 rounds per minute sustained, with brief bursts of 10 rounds possible from ready racks before reload rates declined. Testing protocols began with static firing. A German crew, selected for their Panther experience to provide accurate comparative data, occupied the captured Sherman's crew positions. The gunner settled behind the periscope sight. The loader positioned himself to the left of the breach. The commander observed from the turret cupola, stopwatch in hand, to record precise timing data. The first round loaded smoothly. The breach closed with a solid mechanical click. The gunner acquired a target, a knocked-out French tank hull positioned at 400 meters. The trigger pressed. The gun roared, recoil system absorbing the energy smoothly, while the breech block dropped automatically, ejecting the spent casing. It clattered against the turret basket floor as the loader reached for the next round. 3 seconds elapsed. The second round fired. Another 3 seconds. The third round. The commander's stopwatch continued recording. 4 seconds for the fourth round as the loader adjusted his stance. 3 seconds for the fifth. 3 seconds for the sixth. The ready rack emptied in 20 seconds total, achieving an instantaneous rate of approximately 18 rounds per minute. The German crew paused, unsure whether to trust their observations. 18 rounds per minute exceeded official Panther capability by more than double, approaching rates they associated with smaller caliber weapons. The commander consulted his notes, rechecking calculations. The mathematics remained consistent. They'd just demonstrated fire rates German doctrine suggested impossible for a medium tank gun of this caliber. The loader began replenishing the ready rack from hull storage. This process took longer, requiring him to crouch and reach into the sponson racks, retrieve rounds, and position them in the spring-loaded holders. Approximately 8 seconds per round. The tactical implication became clear. During sustained combat, after expending the ready 6 rounds, the Sherman's practical fire rate would decline to roughly 7 rounds per minute while fighting and reloading simultaneously. But 7 rounds per minute sustained still exceeded official Panther performance specifications. And those initial 6 rounds, deliverable in rapid succession during the crucial opening seconds of an engagement, provided American crews a decisive advantage in any sudden encounter. First shot counted enormously in tank combat. First 6 shots counted even more. German officers present requested additional testing. Perhaps the initial results reflected optimal conditions not reproducible under combat stress. Perhaps crew fatigue would degrade performance significantly. Perhaps the mechanical systems would fail under sustained use. The testing continued through the afternoon, simulating various combat scenarios. The Sherman's gun fired repeatedly, 20 rounds, 30 rounds, 50 rounds. The breech mechanism never jammed. The recoil system never overheated. The fire control remained consistent. German crews rotated through the positions, each confirming the same unsettling conclusions. American automotive engineers had designed this tank for sustained high-tempo operations, prioritizing reliability and ergonomics over theoretical optimization. October 1st, 1944. The technical report reached 7th Army headquarters. Its conclusions, documented facts senior German commanders found difficult to accept. The 76mm Sherman achieved sustained fire rates exceeding German medium tanks by significant margins. The gun proved reliable under extended firing. The ammunition stowage optimized loader efficiency. Most critically, the turret's spacious interior and logical layout enabled rapid crew actions that German designs constrained through cramped working conditions. Panther crews who read these reports experienced profound disbelief. They'd spent months developing tactics based on assumed American limitations. German doctrine emphasized using superior optics and longer-range firepower to engage before American tanks could respond effectively. These tactics presumed German crews could achieve first-round hits at extended ranges and could sustain higher fire rates during close engagements. The captured Sherman data challenged both assumptions. American stabilization systems, though crude by German standards, enabled accurate fire while moving, providing tactical advantages during rapid maneuvering. American ergonomics enabled higher sustained fire rates than German designs achieved. The Panther possessed superior frontal armor and a more powerful gun, but the Sherman compensated through operational advantages German engineers had failed to prioritize. Individual crew accounts from the Aracourt battle provided context for the technical data. Panther gunners reported engaging Shermans at ranges exceeding 1,000 meters, achieving hits, watching their armor-piercing rounds bounce off frontal slopes or punch through side armor, only to face immediate return fire at rates they found shocking. Multiple Panthers reported receiving 4 or 5 hits within seconds of their initial shot, overwhelming their defensive advantages through sheer volume of fire. The psychological impact proved as significant as the material evidence. German tankers had entered the Battle of Aracourt, confident in their technical superiority. The Panther represented Germany's answer to the Soviet T-34, incorporating sloped armor, powerful armament, and advanced fire control. Crews expected to dominate American medium tanks through superior engineering and tactical employment. Instead, they lost approximately 80 Panthers and other armored vehicles during the Aracourt fighting, while American forces suffered significantly fewer losses. Weather conditions prevented German armor from exploiting its range advantages. Close-range engagements in rolling terrain negated German optical superiority. American numerical superiority and aggressive tactical doctrine overwhelmed defensive positions, and American fire rates, consistently higher than expected, prevented German crews from establishing fire superiority even when achieving first hits. Senior commanders struggled to explain these outcomes to subordinates who'd witnessed them directly. The official narrative emphasized American numerical superiority, inevitable given overwhelming industrial capacity. This explanation satisfied political requirements but failed to address tactical reality. German crews knew they'd faced enemy tanks that shot faster, moved more reliably, and operated more effectively under sustained combat conditions than their own supposedly superior vehicles. The captured Sherman became tangible proof that German design philosophy had taken a fundamentally wrong path. German engineers pursued performance specifications, creating vehicles that looked impressive on paper but failed in sustained field operations. American engineers pursued operational effectiveness, creating vehicles that lacked sophistication in many areas but worked reliably under conditions that defeated German equipment. The fire rate disparity exemplified this divergence. German tanks employed manually extracted casings, complex breech mechanisms requiring trained specialists, and ammunition storage arrangements optimized for vehicle protection rather than crew efficiency. These choices reflected engineering priorities, emphasizing theoretical optimization over practical utility. American tanks employed semi-automatic extraction, simplified mechanisms requiring minimal training, and ammunition storage arrangements prioritizing rapid access over marginal protection improvements. November 1944. Additional captured 76mm Shermans reached German testing facilities as Allied forces pushed eastward across France. Each examination confirmed the initial findings. American tank design reflected mature automotive engineering principles applied systematically to military requirements. Reliability, maintainability, and operational effectiveness determined design choices. Theoretical performance advantages took lower priority than sustained field availability. German intelligence officers compiled comparative analysis documenting the capability gap. The data painted a damning picture. Sherman mechanical reliability exceeded Panther reliability by enormous margins. Operational availability rates for American armored units consistently exceeded 60%, while German units struggled to maintain 40%. American tanks completed missions and returned for maintenance. German tanks broke down before reaching objectives or during combat operations. The fire rate advantage compounded these operational disparities. American crews, confident in their vehicles' reliability, employed aggressive tactics, exploiting rapid fire capability. German crews, aware of their vehicles' mechanical fragility, adopted cautious tactics, avoiding sustained high-tempo operations. This tactical divergence reflected accurate assessment of underlying technical realities. Panthers could achieve impressive performance in controlled conditions, but couldn't sustain it during extended combat. Frontline reports from the autumn 1944 fighting across France documented the psychological consequences. Experienced Panther commanders, veterans of Eastern Front combat against Soviet armor, reported feeling genuinely apprehensive about engaging the 76mm Sherman variants, not because American tanks possessed superior armor or firepower, but because sustained engagements consistently favored American crews through higher fire rates and greater operational reliability. The mathematical reality proved brutally clear. A Panther that fired 6 rounds per minute faced a Sherman firing 15 rounds per minute during opening salvos, declining to 7 sustained. The German crew needed to achieve kills with their first few shots because prolonged exchanges guaranteed defeat through volume of fire. American crews could afford to adjust, could afford to miss, could afford to engage at closer ranges where their stabilization provided advantages. This reversal of combat calculus fundamentally undermined German tactical doctrine. Panthers were designed to fight at extended ranges, where their powerful gun and superior optics provided decisive advantages. But weather, terrain, and tactical circumstances frequently forced close-range engagements where Sherman advantages nullified Panther superiority. And even at range, missing the first shot meant facing overwhelming return fire before the German loader could cycle the next round. German tank commanders who survived these engagements described the experience as psychologically devastating. They'd been trained to trust their superior equipment. They'd been told German engineering excellence would overcome Allied numerical advantages. Then they watched American tanks absorb hits that should have been fatal, return fire at rates exceeding German capability, and drive away from engagements that should have destroyed them. The captured Sherman represented all these uncomfortable truths. Every component documented American priorities: robust construction over precise tolerances, simplified maintenance over elegant engineering, crew efficiency over theoretical optimization, operational availability over peak performance. These weren't compromises forced by industrial limitations. They were deliberate choices reflecting mature understanding of armored warfare's operational requirements. German engineers working within an industrial system that prioritized impressive specifications produced tanks that excelled in controlled testing but failed in sustained operations. American engineers applying decades of automotive manufacturing experience produced tanks that lacked technical sophistication in many areas but worked reliably under conditions defeating German equipment. In armored warfare, the weapon that functions consistently beats the weapon that performs brilliantly when operational. December 1944. The Battle of the Bulge provided final confirmation of these lessons under harsh conditions. German forces committed hundreds of Panthers and other armored vehicles to the offensive, achieving initial surprise and tactical success. But operational realities quickly reasserted themselves. Panthers broke down at alarming rates. Supply lines failed to deliver adequate spare parts and fuel. American defenders, many equipped with 76mm Shermans by this stage, fought with confidence born from months of experience. The engagement at Mannheim demonstrated the psychological shift. German SS Panzer forces, attacking at night on Christmas Eve, led their assault with a captured Sherman. American sentries, unable to identify the silhouette in moonlight as hostile, allowed it to approach their positions unopposed. The infiltration worked perfectly, but the subsequent battle, fought at close range under conditions negating German technical advantages, resulted in heavy German losses despite achieving complete surprise. American crews had learned that volume of fire, aggressive tactics, and confidence in their equipment's reliability mattered more than individual technical specifications. German crews, constrained by their vehicles' mechanical fragility and lower fire rates, couldn't exploit tactical advantages when achieved. The Panther remained theoretically superior to the Sherman by most technical measures, but operational effectiveness determined outcomes, and American operational effectiveness exceeded German capability by decisive margins. Post-war analysis by American and British intelligence organizations confirmed what testing of captured Shermans had demonstrated. Systematic examination of German tactical doctrine revealed fundamental misunderstanding of modern armored warfare's operational requirements. German emphasis on individual vehicle superiority blinded them to the critical importance of reliability, maintainability, and sustained availability. They built tanks that impressed observers during demonstrations but disappointed commanders during campaigns. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The fire rate disparity exemplified this misunderstanding. German engineers considered 6 to 8 rounds per minute adequate because they'd optimized their designs for long-range precision engagement. They assumed German crews would achieve kills with initial salvos, making sustained rapid fire unnecessary. This assumption ignored combat reality. Most tank engagements occurred at ranges under 1,000 meters. Many occurred at ranges under 500 meters. Sustained fire capability mattered enormously under these conditions. American engineers understood these realities through extensive study of European combat reports and through consultation with British forces who'd fought in North Africa. They designed the Sherman from its inception for sustained operations under diverse conditions. Fire rate optimization reflected this understanding. The semi-automatic breech, ergonomic ammunition storage, and spacious turret layout all prioritized sustained crew performance over theoretical considerations. The lessons learned through captured Sherman testing influenced German tank design thinking in the post-war Bundeswehr. When the Federal Republic began developing the Leopard 1 main battle tank in the 1950s, designers consciously emphasized reliability and crew efficiency over pure performance specifications. They studied American automotive engineering principles and deliberately applied them to military vehicle development. The resulting Leopard 1 incorporated many design philosophies that made the Sherman successful. The captured 76mm Sherman at Aracourt, designated Butterpanzer 752 inches German documentation, represented far more than enemy equipment brought home for examination. It embodied tangible proof that industrial maturity and practical engineering experience mattered more than theoretical innovation pursued without manufacturing pragmatism. Every test firing demonstrated that American factories could produce weapons German engineers couldn't match through technical sophistication alone. German tank designers pursued advanced specifications because they believed superior technology could overcome material disadvantages and numerical inferiority. They were wrong. American designers built vehicles optimized for operational effectiveness because they understood logistics, maintenance capability, and sustained availability determined victory in modern mechanized warfare. They were right, and their approach proved strategically decisive. The fire rate gap between Sherman and German tanks influenced not just tactical armored warfare, but fundamentally shaped broader understanding of military industrial capacity and its decisive role in modern conflict. Germany entered World War II with technical advantages in many weapons systems, possessing scientific knowledge and engineering expertise exceeding most opponents. However, Germany lacked the industrial depth and manufacturing sophistication to maintain those advantages through sustained mass production while fighting enemies on multiple fronts. The United States entered the war with weapons less technically sophisticated in many respects, but possessed industrial capacity to manufacture them in overwhelming quantities while continuously improving quality, reliability, and performance based on combat feedback. This industrial approach, exemplified by Sherman development and production, proved far more effective than German technical sophistication applied to small-scale production. The mathematics were simple and brutally clear when examined objectively. A Sherman with a 76mm gun, achieving 15 rounds per minute initially and 7 sustained, that reliably reached the battlefield, was infinitely more valuable than a Panther with a superior gun achieving 6 rounds per minute that broke down before engaging or required extensive maintenance between operations. A tank crew confident in their vehicle's reliability fought more aggressively than crews aware their equipment might fail at critical moments. German tankers understood this by late 1944 based on their combat experience. They'd watched American Shermans absorb punishment and continue fighting. They'd engaged American tanks that returned fire at rates exceeding German capability. They'd seen American armored units maintain operational tempo German forces couldn't sustain. But understanding a problem and solving it represent fundamentally different challenges. German industry lacked capacity to retool production around reliability principles, while simultaneously fighting a losing war on multiple fronts against enemies with superior resources. American industry had built reliability into its civilian automotive sector over decades of commercial competition and simply extended those mature principles to military production with remarkable success. The captured Sherman told this entire story through its mechanical simplicity and consistent performance. Every test firing demonstrated American advantages. Every comparison of crew efficiency proved American ergonomic superiority. Every examination of maintenance requirements validated American design philosophy. The tank itself was unremarkable in many ways, one of thousands produced. What it represented proved devastating to German confidence, proof that Germany had already lost the industrial war, even as fighting continued, that American manufacturing capability exceeded German capacity, regardless of technical sophistication or tactical skill. The crews who'd captured and tested this Sherman carried knowledge of American superiority back to their units. They told other tankers about the fire rates they'd witnessed. They described the reliability they'd confirmed. They explained the ergonomic advantages they'd experienced. And gradually, across the front, German tankers adjusted their tactics to reflect uncomfortable realities about enemy capabilities that official propaganda refused to acknowledge. By early 1945, American Sherman units routinely engaged German armor at ranges and under conditions that would have been suicidal months earlier. Crews fought with confidence born from experience and validated by results. They'd learned their tanks could win engagements through sustained fire rates, reliable operation, and aggressive tactics. Technical specifications mattered less than operational effectiveness, and American operational effectiveness exceeded German capability by margins that determined strategic outcomes. The captured 76mm Sherman, sitting in a German motor pool with hastily painted crosses covering American stars, represented the end of German tank crew confidence in their technical superiority. Every mechanical component demonstrated American industrial maturity. Every design choice revealed priorities German engineers had failed to understand. Every test confirmed that American automotive excellence had created a weapons system German industry couldn't match through innovation alone. The fire rate advantage, so difficult for German crews to accept initially, became the defining characteristic of Sherman effectiveness. Not armor thickness, not gun caliber, not optical quality. Fire rate, the ability to put rounds on target consistently and repeatedly. The capacity to sustain combat tempo, while German tanks paused to reload. This seemingly mundane advantage, achieved through ergonomic design and semi-automatic mechanisms, proved more decisive than any amount of theoretical performance superiority. The testing protocol expanded beyond simple static fire exercises. Major Klaus Becker, the 111th Panzer Brigade's chief gunnery instructor, insisted on replicating combat conditions as accurately as possible, without risking the captured vehicle's destruction. He'd fought through France in 1940 and participated in the initial phases of Operation Barbarossa. His experience taught him that laboratory conditions produced meaningless data. Real combat imposed stresses that revealed truth about equipment performance in ways controlled testing never could. Becker ordered his team to establish multiple target arrays at varying ranges. Wooden frames wrapped in canvas simulated enemy tanks at 200, 400, 600, and 800 meters. The crew would engage targets in sequence, simulating a rapid encounter engagement where multiple enemy vehicles appeared simultaneously. This scenario occurred frequently in the bocage fighting and urban combat characterizing Western Front operations in late 1944. The German gunner, Unteroffizier Hans Richter, had served in a Panther crew for 8 months. He understood his own tank's capabilities intimately. He'd engaged American Shermans on at least 15 occasions, destroying 7 confirmed. His muscle memory was trained for the Panther's recoil characteristics, sight picture, and reload rhythm. Now he occupied an American tank, about to test whether his assumptions about enemy capabilities matched reality. The exercise began at Becker's signal. Richter acquired the first target at 200 meters, a ridiculously close range by German training standards but increasingly common in actual combat. The trigger squeezed. The gun fired. Recoil rocked the hull slightly. The breech dropped automatically, ejecting the spent casing with a metallic clang. The loader, Gefreiter Paul Schneider, already had the next round moving toward the breech before the empty casing stopped bouncing across the turret floor. Second target, 400 meters. The turret traverse motor whined smoothly as Richter adjusted aim. Less than 2 seconds to acquire and stabilize. Fire. The spent case ejected. Third round loading. Richter shifted to the 600-meter target. The hydraulic turret traverse felt responsive, almost effortless compared to the Panther's system, which required more deliberate input. Fire. Fourth round. The closest target again, simulating an enemy vehicle that had been obscured initially. Fire. Fifth round. The 800-meter target. Fire. Sixth round. Back to 400 meters. Fire. Becker's stopwatch showed 23 seconds elapsed. 6 targets engaged at varying ranges, requiring turret traverse and sight picture adjustment between each shot. Under similar conditions in his Panther, Richter estimated he might achieve 35 to 40 seconds for the same engagement sequence, possibly faster if everything went perfectly. But things rarely went perfectly in combat. The ready rack sat empty. Schneider immediately began replenishing from the hull racks, working methodically. The exercise continued with Richter engaging targets as rounds became available. The sustained fire rate dropped considerably, exactly as predicted, but even this reduced tempo exceeded what Richter considered normal for his Panther. The ergonomic layout made an enormous difference. The loader didn't have to contort his body awkwardly. The ammunition racks positioned themselves within easy reach. The turret basket provided stable footing. After expending 20 rounds, Becker called a halt. The crew climbed out, sweating despite the cool autumn air. Richter pulled off his padded headset and lit a cigarette with shaking hands. Not from fear or exhaustion, from recognition. He'd just experienced firsthand why American tank crews fought with such aggressive confidence. Their equipment enabled tactics German crews couldn't safely employ. Becker gathered his testing team for immediate analysis before proceeding. The stopwatch data required verification against expectations. The initial 6-round burst in 23 seconds, including time for turret traverse and target acquisition, demonstrated combat effectiveness far exceeding official intelligence assessments of Sherman capabilities. More troubling, the sustained rate while reloading from hull racks suggested American crews could maintain pressure during extended engagements in ways German doctrine didn't account for. The afternoon testing grew more complex. Becker designed a scenario replicating the chaos of meeting engagements where friendly and enemy vehicles intermixed. Targets at varying ranges would be designated hostile or friendly in random sequence. The crew would engage only hostile targets while avoiding friendly fire. This tested not just mechanical fire rate but crew coordination and decision-making under pressure. German-colored panels marked friendly targets. Enemy targets remained unmarked. The exercise emphasized that raw fire rate meant nothing without accurate target discrimination. Superior fire rate became a liability if it encouraged indiscriminate shooting. American training doctrine presumably addressed this through crew drills and fire discipline. The German crew would attempt to maintain comparable discrimination standards while maximizing tempo. The scenario proved enlightening. Richter found the commander's override system particularly effective. Obergefreiter Martin Weber, serving as tank commander for this exercise, could designate targets verbally, while Richter maintained situational awareness through his periscope. The intercom system, though simpler than German designs, provided adequate clarity. More importantly, the turret layout allowed natural communication through proximity and line of sight. They engaged 12 targets over 90 seconds, correctly identifying and engaging 8 hostile targets while avoiding 4 friendlies. 0 friendly fire incidents. Richter estimated comparable performance in his Panther would require at least 2 minutes, probably longer. The difference stemmed not from superior German gunnery skills, but from mechanical and ergonomic advantages built into the American design. Becker introduced thermal stress testing. The gun had now fired approximately 40 rounds over several hours. Metal components had heated and cooled repeatedly. Tolerances had expanded and contracted. Combat operations rarely allowed weapons to cool completely between engagements. The Sherman would now fire 30 rounds in rapid succession to simulate sustained action during a breakthrough operation, where American armor might engage multiple defensive positions sequentially. The crew remounted. Schneider positioned himself with hull racks fully stocked. Weber coordinated the fire sequence. Richter prepared mentally for sustained operations. The exercise would test not just mechanical reliability but human endurance under repetitive stress. Combat fatigue degraded performance significantly. The question was how much, and whether American ergonomic design reduced that degradation. The firing commenced, round after round. The breech mechanism cycled continuously. Spent casings accumulated rapidly in the turret basket floor, requiring Schneider to kick them aside periodically to maintain footing. The recoil system absorbed energy consistently, without apparent degradation. The gun mount remained stable. The sight picture stayed clear despite vibration and heat shimmer. Richter's shoulder began aching from repeated recoil impact against the padded rest. His eyes burned from concentration, and cordite fumes accumulating in the turret despite ventilation. His ears rang despite the padded headset. But the mechanical systems never faltered. The breech never hesitated. The ammunition never jammed. The traverse never stuttered. American engineering had built endurance into every component. After expending 30 rounds, Becker called another halt. The gun barrel glowed faintly in the late afternoon shadows, heat radiating visibly. German doctrine warned against sustained fire at these rates, with the Panther's 75mm KUK-42, citing barrel life concerns and accuracy degradation. Yet the Sherman's barrel showed no obvious distress. The rifling presumably remained intact. American metallurgy and manufacturing quality ensured durability under conditions German guns couldn't sustain. The final test scenario addressed the question troubling every German officer present. Could American crews actually achieve these performance levels in combat, or did they represent artificial laboratory conditions impossible to replicate under fire? Becker designed a stress test incorporating multiple complications simultaneously. The crew would engage targets while experiencing simulated battle damage, communication failures, and time pressure. Weber would relay target information using hand signals only, simulating intercom failure. Richter would engage targets while Schneider created deliberate disruptions, bumping into him at random intervals to simulate hull movement and terrain effects. The gunner's periscope would be partially obscured with mud, reducing visibility. All of this while maintaining rapid fire against multiple targets, appearing in unpredictable sequence. The chaos began. Weber's hand jabbed, right, indicating a target. Richter traversed, acquired through the smeared optic, fired. Schneider deliberately jostled him while loading the next round. Another hand signal from Weber. Richter compensated for the contact, traversed left, fired. The rhythm felt jerky and uncomfortable compared to earlier exercises, yet rounds continued finding their marks. The mechanical systems absorbed human error and environmental stress that would have created serious problems in more temperamental designs. The German crew, all experienced Panther veterans, completed the exercise with grudging respect. They'd fought against Shermans for months, destroying dozens. They'd developed tactical countermeasures based on assumed limitations of American equipment. Those assumptions now lay shattered across the testing ground, along with spent shell casings. The implications extended beyond tactical considerations. If American tank crews could actually perform at these levels in combat, and if thousands of Sherman tanks equipped entire armored divisions, then German tactical advantages through superior firepower and armor protection might not matter strategically. Quantity and reliability, properly applied, could overwhelm quality if the quality gap wasn't sufficiently large, and the testing demonstrated that gap had narrowed considerably. Becker compiled his report that evening by lantern light in a commandeered farmhouse. The data told an unambiguous story. The Sherman 76mm variant possessed fire rate capabilities exceeding German medium tanks by substantial margins. More concerning, these capabilities derived from systematic engineering decisions prioritizing operational effectiveness over theoretical performance. American designers understood modern armored warfare better than German intelligence had credited. The report would travel up the chain of command, reaching 7th Army headquarters within days. Becker included specific recommendations for tactical adjustments. German crews should avoid extended engagements with Sherman 76 variants when possible. The American fire rate advantage became decisive in sustained combat, better to maneuver for flank shots enabling single-shot kills rather than trading fire directly. Accept that American tanks could put more rounds downrange more quickly. Adapt tactics accordingly. But tactical adjustments couldn't address the deeper strategic problem the testing revealed. American industry produced thousands of tanks embodying mature automotive engineering principles. German industry produced fewer vehicles, incorporating advanced technology but lacking manufacturing refinement. In a war of attrition, manufacturing maturity and production volume mattered more than individual vehicle superiority. The mathematics were unforgiving. The captured Sherman, now parked under camouflage netting after its day of intensive testing, represented a watershed moment in German understanding of American military-industrial capability. Before this testing, German tankers could maintain confidence in their technical superiority, even when outnumbered. After this testing, that confidence eroded. They'd experienced American advantages firsthand, not through propaganda or intelligence reports, but through direct physical interaction with enemy equipment. Word spread through the Panzer units organically. Crews who'd participated in the testing told others. The specifics of fire rate comparisons and ergonomic advantages passed through informal networks. German tankers began reassessing their tactical approaches based on this new understanding. They fought more cautiously against Sherman 76 variants. They prioritized different engagement methods. They adjusted their expectations about encounter outcomes. The psychological impact extended beyond immediate tactical considerations. German soldiers had entered the war believing in their technological and organizational superiority. That belief sustained morale through early victories and later setbacks. But physical evidence of American industrial maturity, embodied in a single captured tank, undermined that sustaining narrative. If American equipment matched or exceeded German capability in critical performance measures, what justified continued resistance against overwhelming material odds? Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.